Ladies and gentlemen, today we take a moment to delve into the remarkable life of a person whose genius spanned across multiple fields, from mathematics to physics, and whose contributions laid the groundwork for many aspects of modern science. His journey was one marked by intellectual brilliance, groundbreaking discoveries, and a profound exploration of both the natural world and the human condition. Born in the early 17th century, the individual who would go on to become one of the most influential thinkers in the history of science and philosophy had a childhood marked by both privilege and tragedy. He was born in a small town in France in 1623. To a family with a rich intellectual and cultural background. His father, Etienne Pascal, was a respected lawyer who valued education and intellectual pursuits, while his mother's early death left a lasting emotional impact on him. Though only 3 years old at the time of her passing, the absence of his mother left a profound sense of loss in his life. His early years were spent in a nurturing environment that fostered learning. His father, recognizing his son's potential, took on the responsibility of overseeing his education. He ensured that his son received a well-rounded intellectual foundation, focusing on classical education, including Latin, Greek, and the study of philosophy. However, he also provided a unique environment for his son by promoting an early introduction to more specialized fields of study, including mathematics and the sciences, subjects that were still in their early stages of development. What truly distinguished his education from that of his contemporaries was his father's approach to learning. Etienne Pascal removed his son from formal schooling at an early age, which, although unusual for the time, allowed the young boy to develop a more independent and self-guided approach to his intellectual growth. While other children of his age were confined to conventional educational structures, he was encouraged to explore subjects at his own pace, giving him the freedom to explore areas that piqued his curiosity. It was during his teenage years that his prodigious abilities became more apparent. At the age of 12, he had already begun studying Euclid's Elements on his own, a complex work of geometry that laid the groundwork for much of modern mathematics. By the age of 16, he had developed his first mathematical theorem, a groundbreaking discovery in the field of geometry, one that would later establish him as a rising star in the intellectual circles of Paris. This early achievement was not simply a matter of academic success, but a demonstration of a mind capable of seeing mathematical relationships in ways few others could. Despite his precociousness, his education was not limited to formal academic study. His intellectual curiosity was wide-ranging, extending to a variety of fields, including theology, physics, and philosophy. His father encouraged him to engage in discussions about these topics, despite the fact that many of his contemporaries would not even begin to explore such areas until much later in their lives. He also experienced the personal challenges of growing up in a time of great religious and political upheaval in France, with the 30 Years' War and internal conflicts shaping the intellectual landscape of the era. These turbulent times shaped his worldview and inspired a deep sense of inquiry into the nature of human existence, the universe, and the divine. His education, while unique, was also marked by moments of solitude and reflection. He was often introspective, contemplating not only the complex mathematical and scientific problems that fascinated him, but also larger existential questions that would later find expression in his philosophical writings. This combination of early academic rigor and deep introspection created a fertile ground for the development of a mind that would leave a lasting mark on history. Thus, from an early age, his life was shaped by a distinctive blend of privilege, loss, and intellectual stimulation. His education was both structured and independent, fostering a mind that would go on to break new ground in multiple fields. At the tender age of 16, the young scholar embarked on a path that would soon alter the course of mathematical history. His first significant breakthrough in mathematics occurred when he turned his attention to the field of geometry. a discipline that had long been established by ancient Greek scholars, most notably Euclid. However, this teenager's approach to geometry would be anything but conventional. While many of his peers were still grappling with the basics, he ventured into complex problems that would challenge even the most advanced thinkers of his time. His groundbreaking work was centered around a subject that had, for the most part, remained relatively static for centuries: projective geometry. This branch of geometry deals with the properties and relationships of geometric figures as seen from different perspectives or points of view. Rather than adhering strictly to the traditional geometric methods of the time, which focused on Euclidean principles of flat, two-dimensional space, he explored geometrically from a more abstract perspective. His investigations into the nature of conic sections, figures such as ellipses, parabolas, and hyperbolas, became a central point of focus. The crucial breakthrough came when he made a profound discovery about the properties of these conic sections. He recognized that there existed a deeper, more fundamental relationship between these shapes than had been previously understood. His work revealed that certain geometric properties of conic sections could be understood not just in terms of their physical construction, but in terms of abstract points and lines that were often beyond the scope of traditional geometry. His innovative thinking opened up new pathways for mathematicians to explore. One of the most important aspects of his contribution to geometry was the way he introduced the concept of the projective plane, a way of thinking about geometry that was revolutionary for its time. In this new framework, the usual boundaries of Euclidean space were discarded in favor of an approach that allowed for the extension of geometric principles beyond traditional two-dimensional space. The idea of a projective plane essentially proposed that lines and points could extend infinitely, thus offering a way to think about geometrical objects and their properties from a wider, more flexible perspective. This early work also led to an innovative mathematical tool, Pascal's theorem, which would become a fundamental part of projective. The theorem demonstrated a relationship between 6 points on a conic section, which, when connected by lines, created a hexagon where certain intersections of lines had predictable and geometric properties. This was an important step in the development of projective geometry, as it provided a specific and testable example of how abstract geometric properties could be applied and understood through real-world constructions. His contribution to geometry wasn't just about solving existing problems, but about radically reshaping the way people thought about space, lines, and shapes. His work demonstrated the power of abstraction and how looking at familiar objects through a different lens could lead to new insights. It would not be an exaggeration to say that his approach to geometry set the stage for later developments in both mathematics and physics, influencing the works of future mathematicians and physicists, including those who would later contribute to the development of non-Euclidean geometry and the field of topology. His breakthrough was not merely a testament to his intellectual ability, but also a reflection of his unique approach to learning. His ability to absorb complex material at a young age and apply it in novel ways was indicative of a mind that was not just absorbing existing knowledge, but actively pushing the boundaries of human understanding. His early work in geometry left an indelible mark on the field and paved the way for many future advancements that would follow in the centuries to come. As his mathematical and intellectual journey continued, his interests expanded beyond the realm of abstract geometry and into the physical world, where he made profound contributions to the fields of fluid mechanics and hydrostatics. His work in these areas was not only groundbreaking for its time, but laid the foundation for many principles that are still used in engineering and physics today. So, the key to understanding his contributions to fluid mechanics begins with his fascination with the nature of fluids and their behavior under different conditions. In the mid-1640s, while still in his 20s, he turned his attention to the study of liquids and gases, specifically exploring the behavior of liquids in confined spaces. During this period, he became deeply engaged in solving the fundamental problems posed by the behavior of fluids under pressure. One of his most significant contributions to fluid mechanics was the formulation of what became known as Pascal's principle, or the principle of transmission of fluid pressure. This principle states that when a change in pressure is applied to an enclosed fluid, the pressure change is transmitted equally and undiminished throughout the fluid, in all directions. In simpler terms, it means that if you apply pressure to a confined liquid, that pressure will be uniformly distributed across the liquid, affecting all parts of the container equally. This discovery had far-reaching implications, particularly in the fields of engineering and hydraulics. It led to the development of the hydraulic press, a machine capable of lifting heavy weights using small amounts of force. One of the earliest applications of the principle in practical technology. Pascal's principle also became crucial for understanding the functioning of a wide range of devices, from hydraulic lifts to brake systems, and even the workings of modern machinery and vehicles that rely on fluid systems. At the same time, his investigations into the nature of air pressure and the properties of gases led to the formulation of what we now call Pascal's law. His experiments with a barometer, a device used to measure atmospheric pressure, helped establish the relationship between the height of a column of mercury and the pressure exerted by the atmosphere. Through these experiments, he demonstrated the existence of a vacuum and provided clear evidence that air had weight and exerted pressure, a concept that was not widely accepted at the time. One of the most famous of his experiments involved a venture to the top of a hill in the French countryside, where he and his colleagues carried a barometer. By comparing the mercury levels at higher altitudes to those at sea level, he demonstrated how atmospheric pressure decreases as altitude increases. This experiment not only confirmed the theory of atmospheric pressure, but also helped lay the groundwork for the later development of the study of gases and fluid dynamics. In many ways, this experiment is viewed as a pivotal moment in the development of modern physics, as it provided key empirical evidence for the behavior of fluids and gases. Pascal's fascination with the natural world extended beyond theoretical principles to practical experiments, often involving direct observation and hands-on investigations. His approach to fluid mechanics was not only theoretical but deeply experimental, marking a shift in scientific inquiry during a time when many scientific investigations were still grounded in philosophical or purely mathematical reasoning. By combining abstract theory with empirical testing, he was able to bridge the gap between thought and application, influencing later scientists like Isaac Newton and Robert Boyle, who would further develop theories related to gases and fluids. His contributions also intersected with the field of hydrostatics, which deals with the study of fluids at rest. By examining how pressure behaves within a fluid at rest and how fluids respond to external forces, Pascal's research contributed to a more nuanced understanding of the properties of liquids and gases. He explored the relationship between pressure, density, and volume, leading to a greater understanding of how fluids behave under various conditions. Through his work on fluid mechanics and hydrostatics, he had not only demonstrated remarkable scientific insight, but also provided practical tools for industries that would later rely on his discoveries. The hydraulic press, for example, became a critical invention for both early industrialization and the development of machines that could perform tasks previously impossible with manual labor. In sum, his advancements in fluid mechanics and hydrostatics were not just theoretical breakthroughs, but practical, real-world innovations that continue to impact the fields of engineering, physics, and many other disciplines today. His work helped redefine the way scientists understood the nature of forces, pressures, and the behavior of fluids, and his discoveries paved the way for the modern understanding of mechanics and thermodynamics. As his intellectual pursuits continued to span diverse fields, one of his most notable achievements came in the realm of applied mathematics and engineering, the invention of the Pascalin, a mechanical calculator. This invention, created in the early 1640s, was a testament to his ingenuity and his desire to bridge the gap between abstract mathematical theory and practical application. The Pascaline holds the distinction of being one of the first mechanical devices capable of performing arithmetic calculations, and it marks a pivotal moment in the history of computational devices. The story behind the Pascaline begins with his deep frustration over the tedious and error-prone process of manual calculation. At the time, mathematicians, merchants, and engineers often relied on human calculators to perform complex arithmetic, particularly multiplication and division. These calculations were not only time-consuming but also prone to mistakes, leading to delays and inaccuracies in a wide range of activities, from scientific experiments to business transactions. Motivated by the desire to alleviate this burden, he sought to develop a machine that could perform calculations with speed and precision. Drawing upon his extensive knowledge of mathematics, mechanics, and physics, he devised a machine that could perform addition and subtraction using a series of rotating wheels and gears. The device, which consisted of a series of interlocking gears with decimal-based dials, was capable of carrying out addition and subtraction directly by turning a series of dials. Each dial represented a single digit of a number, and as one dial turned, the others would adjust accordingly to keep the calculations in sync. For instance, when the dial for 9 was turned, the next digit would automatically roll over to 0 and carry a value over to the next column, mimicking the way humans perform carrying operations in arithmetic. The Pascaline worked by employing a mechanical system of gears and wheels that functioned similarly to modern calculators. The gears were connected to a series of wheels that were each marked with digits from 0 to 9, and each wheel represented a place value, units, tens, hundreds, and so on. By turning the dial, a user could input numbers and the machine would perform basic arithmetic operations with remarkable efficiency. Despite its innovation, the Pascaline was not without its challenges. One of the difficulties lay in the mechanical complexity of the device. The gears and wheels had to be precisely constructed to ensure accuracy and smooth operation. Furthermore, the machine was cumbersome and early versions were somewhat bulky, making it difficult to transport. Additionally, while the Pascaline was capable of performing addition and subtraction with relative ease, it was less effective for multiplication and division, which required multiple steps to be carried out manually. Nevertheless, the invention of the Pascaline was a monumental achievement for its time. It represented one of the first instances of mechanized computation, providing a glimpse into a future where machines could assist humans in performing complex tasks. His invention was so ahead of its time that it would take centuries before similar mechanical calculating devices would become widespread. The invention was a precursor to the modern computer and laid the groundwork for future developments in automation and computational technology. The Pascaline was not an instant success, however. The device was primarily designed for personal use, and Pascaline only built a small number of machines, some of which he sold to merchants and business. Despite its potential, the Pascaline faced resistance due to its complexity, high cost, and the fact that it was not yet widely accepted by society. Many people were skeptical of the need for such a machine, and some saw it as an unnecessary luxury. Furthermore, the mechanical limitations of the device meant that it was not fully capable of solving all mathematical problems, limiting its practicality. While the Pascaline itself did not become a commercial success in its own time, its impact was far-reaching. The concepts it introduced laid the foundation for the development of more advanced calculating machines in the future. The idea of mechanizing calculation and using gears, wheels, and dials as a means of automating arithmetic would eventually inspire other inventors and engineers, such as Charles Babbage, who is often credited with designing the first true mechanical computer, and Gottfried Wilhelm Leibniz, who independently developed similar calculating machines. Anderson, the Pascaline also sparked an interest in automating calculations, which would later evolve into the computational devices that form the backbone of modern technology. It demonstrated the potential for mechanical devices to assist humans in carrying out intellectual tasks, and in doing so, it served as a precursor to the digital age. Although the Pascaline was not widely adopted during Pascal's lifetime, its legacy would live on in the work of later innovators, and its design principles would continue to influence the development of more sophisticated calculators and computers. In essence, the invention of the Pascaline was a monumental step forward in the history of technology. It was not simply a tool for performing calculations. It represented the merging of mathematical theory with practical engineering, a concept that would continue to drive innovation in fields ranging from computing to automation. Pascal's creation was a pioneering work that foreshadowed the future of mechanical computation and technology, influencing the development of the tools that have revolutionized the modern world. While he is perhaps most widely recognized for his contributions to mathematics and physics, his intellectual pursuits also extended deeply into philosophy and the human condition. In his later years, he became increasingly fascinated with existential questions that transcended the confines of science and mathematics, exploring the mysteries of faith, reason, and the human experience. His philosophical reflections would go on to form one of the most influential bodies of work in Western thought, particularly through his posthumously published collection, Pensées. His philosophical journey was deeply shaped by the turbulent religious and political context of 17th century France. During his lifetime, Europe was embroiled in religious wars and philosophical debates about the nature of God, human existence, and reason. Pascal, born into a Catholic family, was profoundly affected by the theological divisions of his era, especially the contrast between the rigorous intellectualism of the Jansenist movement, of which he was a part, and the more liberal, worldly approach of the broader society. These tensions in the intellectual and spiritual world were key factors that directed him toward questions about human existence and the relationship between faith and reason. One of the most compelling aspects of his philosophy is his exploration of the duality of human nature. Pascal was keenly aware of the contradictions and complexities of being human. On one hand, humans have a remarkable capacity for reason and intellect. On the other hand, they are marked by weakness, imperfection, and a tendency to err. He believed that while humans are capable of great intellectual achievements, they are also frail and subject to the randomness of fate, which creates a tension between pride in human accomplishment and a recognition of the limitations of human existence. This paradox would form the basis of much of his philosophical thought. Central to his view of the human condition was the idea of diversion, the tendency of human beings to distract themselves from confronting the true meaning of life and the inevitability of death. Pascal argued that much of human life is consumed with distractions, pleasures, comforts, and even intellectual pursuits, designed to keep individuals from thinking about deeper existential questions. This, he believed, was a fundamental flaw in human nature. Rather than facing the reality of our mortality and the mysteries of existence, people often escape into distractions, refusing to confront the infinite void that defines human life. For Pascal, this avoidance of reality was a form of denial, preventing individuals from achieving true spiritual and intellectual insight. In this sense, his philosophy was deeply rooted in a sense of existential urgency. And so the word existence, soup for the soul, he saw human life as fragile and fleeting, an idea that was informed by his own struggles with illness and the constant threat of death. His reflections on human suffering, vulnerability, and the inevitability of death made him acutely aware of the limits of human agency. Pascal was deeply concerned with the question of how one should live in the face of these uncertainties, particularly in relation to faith. He felt that human reason alone could not provide sufficient answers to life's most profound questions, especially when it came to matters of God, the afterlife, and the nature of existence. This philosophical questioning culminated in his famous Pascal's wager, a provocative argument for belief in God based on reason rather than direct evidence. Pascal argued that given the uncertainty surrounding the existence of God, it is far more rational to wager on God's existence rather than risk the consequences of disbelief. In essence, if you believe in God and God does not exist, you lose little. But if you do not believe in God and God does exist, the stakes are immeasurably high. Eternal damnation. Thus, belief in God becomes a rational choice not because of certainty, but because the consequences of faith are potentially far less risky than the consequences of doubt. Pascal's views on faith were also shaped by his belief in the necessity of grace, the idea that humans cannot come to understand God through their own efforts or intellect. But he viewed human reason as inherently limited in its ability to comprehend the mysteries of existence, particularly when it came to matters of salvation and the afterlife. For Pascal, faith was not the result of human logic. Rather, it was a gift that transcended human understanding, something that could not be grasped by reason alone. This idea would later resonate with existential thinkers and theologians, who would expand on the concept of faith as a leap beyond the limitations of human understanding. Pascal's reflections on the human condition were also steeped in a sense of the absurd. He was aware of the vastness of the universe and the apparent insignificance, yet paradoxically he believed that humans, despite their frailty, were also capable of understanding their place in the universe, even if this understanding was incomplete. In this tension between the finite and the infinite, between the fragility of human life and the grandeur of the cosmos, Pascal saw a unique opportunity for human beings to reflect on their existence and their relationship with the divine. For him, true wisdom lay in recognizing both the greatness and the futility of human existence, and in humbling oneself before the mysteries that lay beyond human comprehension. Ultimately, Pascal's philosophical legacy rests on his exploration of the limits of human reason, the necessity of faith, and the paradoxes inherent in his reflections on the human condition, marked by a deep understanding of both the dignity and the fragility of human life, continue to resonate with modern thinkers. His ability to confront the profound uncertainties of existence while searching for meaning in the face of those uncertainties remains one of his most enduring contributions to philosophy. Through his work, he gave voice to the struggles of the human spirit in the search for truth, meaning, and redemption, making his insights as relevant today as they were in the 17th century. Blaise Pascal's legacy and influence extend far beyond the brief span of his life, reaching across the centuries and touching numerous. Though his life was tragically short, he passed away at the age of 39. His profound contributions have had a lasting impact, shaping the intellectual landscape in ways that continue to reverberate in the modern world. One of Pascal's most significant legacies lies in his work in mathematics, where he helped to pioneer the development of probability theory. In addition, Pascal has had an amazing impact. Alongside Pierre de Fermat, Pascal laid the groundwork for what would later become one of the most important branches of mathematics. Their correspondence in the 1650s on the problem of points, the issue of how to divide stakes in an unfinished game of chance, produced groundbreaking ideas about the mathematical treatment of randomness, uncertainty, and chance. This work formed the foundation for probability theory, which would become central to fields ranging from statistics and economics to computer science and finance. His insights into probability have become integral to understanding the randomness inherent in everything from games of chance to scientific predictions and the behavior of financial markets. In addition to his contributions to probability, Pascal's work in fluid mechanics and hydrostatics had far-reaching implications in the development of modern engineering. His Pascal's principle, which states that pressure applied to an enclosed fluid is transmitted equally in all directions, became a cornerstone of hydraulic engineering. This principle is foundational in the design of hydraulic systems used in machines, vehicles, and various industrial applications. The hydraulic press, for example, which was based on Pascal's work, enabled a wide range of innovations, from lifting heavy objects to powering various machinery. His research on the nature of fluids and air pressure also advanced the understanding of vacuum theory, helping to shape early modern physics. His experimental methods and careful observations marked a departure from purely theoretical speculation, influencing later scientists like Isaac Newton, who would build on his discoveries to develop the foundations of classical mechanics. Pascal's invention of the Pascaline, one of the first mechanical calculators, is another area where his legacy continues to resonate. Though the Pascaline itself was not widely adopted during his lifetime, it paved the way for the development of more sophisticated calculating machines and ultimately the modern computer. In creating a mechanical device to assist in arithmetic calculations, Pascal was an early pioneer of automation and computation, anticipating the future of technology by centuries. The ideas embedded in the Pascaline influenced later innovators such as Charles Babbage, whose analytical engine laid the foundation for modern computing. Today, Pascal's work is remembered as a precursor to the digital revolution, highlighting his visionary contributions to the future of technology. Beyond the realm of mathematics and science, Pascal's philosophical and theological writings also left a profound legacy. His work, Pensées, translated as Thoughts, remains one of the most significant texts in the history of philosophy. In this collection, he wrestles with the nature of faith, reason, and the human condition, offering profound insights into the limits of human understanding and the necessity of divine grace. Pascal's reflections on the duality of human existence, the tension between reason and faith, the infinite and the finite, have had a lasting impact on Christian thought, particularly in the tradition of existential theology. His ideas about human frailty, the need for redemption, and the paradoxes of existence influenced later thinkers like Søren Kierkegaard, who would build upon Pascal's existential concerns in his own writings. Pascal's most famous argument, Pascal's wager, which posits that belief in God is the most rational bet given the uncertainties of existence, remains a staple in discussions of religious philosophy and the philosophy of religion. The wager highlights the practical necessity of faith, proposing that, even in the absence of empirical proof, belief in God can be seen as a rational choice based on the potential consequences of both belief and unbelief. This argument has sparked countless debates and discussions about the relationship between faith, reason, and evidence, and continues to be a key topic of study in both philosophical and theological circles. His legacy is also felt in the broader realm of scientific method. Pascal's approach to experimentation and empirical inquiry, particularly in his studies of fluids and pressure, helped to establish a more rigorous, evidence-based approach to scientific investigation. His insistence on observation and experimentation laid the groundwork for the development of modern experimental science, influencing the likes of René Descartes, Isaac Newton, and others who were instrumental in the scientific revolution. The Pascal programming language, which emerged in the 1970s, is a direct homage to his name and his contributions to the development of early computing. Designed by Niklaus Wirth, Pascal was intended to be a simple and efficient language for teaching programming, and it became one of the most widely used programming languages in the 1980s. Though other programming languages have since overtaken Pascal in popularity, its role in the history of computer science remains significant, further cementing his place in the development of modern technology. Today, Pascal's influence continues to shape a wide range of disciplines. In mathematics, his work in probability theory and geometry continues to be studied and built upon. In engineering, his principles are foundational to the design of hydraulic systems and machines that rely on fluid dynamics. In computer science, his contributions to the development of early calculating machines have left an indelible mark. In philosophy and theology, his existential reflections and insights into the human condition continue to provoke thought and inspire new generations of thinkers. What makes Pascal's legacy so enduring is the breadth and depth of his contributions. His genius lay not only in his ability to excel in various fields, but in his ability to see the connections between them. He was a true polymath, a thinker who understood that the boundaries between mathematics, science, philosophy, and religion were not always fixed, but often overlapped and informed one another. His work remains a beacon for anyone seeking to understand the intricate connections between reason, faith, and the world around us. In closing, while his life was brief, the depth of his contributions speaks volumes about his genius, curiosity, and relentless pursuit of knowledge. His legacy remains a testament to the power of human intellect, one that continues to guide and challenge us today. Thank you.